Hello, Stat 135 friends. This is a summary from lecture 6. So last time we talked all about Fisher information, and I'm just writing out all of the main results here. Today what we're going to do is practice with Fisher information and MLE, as well as talk about sufficient statistics. So we started with a warm-up. So we have x1 to xn IID Poisson with, to recall, that is a discrete distribution with the following probability mass function. And I asked you to compute the Fisher information and a 90% CI. So when you're computing the Fisher information, remember that Fisher information is about the information in a single observation. So we only have a single x. So when we're computing our log likelihood, you're not going to have the sum of x. You're going to have just, or x1 to xn, you're going to have x, a single observation. Then you take the first and second derivative and find the expectation, and we found that the Fisher information is 1 over lambda. Then to find a 90% CI, when we're told that the MLE estimate for lambda is 5, well, we know that the MLE estimate for large N is normal lambda 1 over N Fisher information. So I just wrote out what that means according to our calculations above. And yeah, that's all there is to that. Now, Fisher information is about information from a single data observation, but you can ask, what's the information from an IID random sample? And so I just basically derived that the Fisher information from n IID observations is just n times the Fisher information of a single observation. So that the proof is very easy. So also just note that the notation for information from the sample is in theta. Compare that with I theta for a single observation. So here we can write in theta, since that's the same as ni theta. And then we did another example where we looked at x1 to xn IID random sample with density theta x to the theta minus 1. And we found the ML estimate, the sample Fisher information, what distribution the ML estimate is approaching, and an approximate CI for large N. So calculation of the ML estimate is straightforward, although of course carrying it out, people had difficulty calculating derivatives and not making silly algebra mistakes, but the ideas are fairly easy. The sample Fisher information. So here now, when we're calculating the sample Fisher information, we can actually use this calculation here. so you can use this because we found the derivative of the log likelihood for our sample, and so all we need to do is take this second derivative of this, which I've done here, and then you can calculate the sample Fisher information. Easy peasy. And then what distribution is this approaching as n gets large? Well, it's normal theta 1 over in theta. So that, and then here we can write out the CI. Good. And then we discussed mean squared error. So this is one way that's used to measure how good an estimator is. So you want it to have a small MSE. And the definition of MSE is it's the expectation of of the estimator minus theta quantity squared. And that can be written out as a multiple integral, but we don't actually ever solve this integral. Instead, we use this theorem here, which you're going to, I think, prove for a homework, which says that the MSE is the variance plus the bias squared, where the bias is the expectation of the estimator minus theta. So bias is 0 when your expectation of the estimator is theta itself. You should put here a parenthesis. That. I will. Oh, I guess I should just show you the picture of what MSE represents here. So MSE is basically the average deviation between your estimator and theta. So you have theta hat has a distribution. You have theta, and so what's the average? What's the average distance between those? And so you can sort of tell it just from the picture. Most of the distribution is around in here, right? There's some out further in the tails, but on average, the distance of theta hat from theta is, it looks like it's about that distance. Okie doke. So really MSE, if MSE is variance plus bias squared, then you have a competition between, you want the MSE to be as small as possible, but that doesn't necessarily mean that you have an unbiased estimator that's going to be best for you. So you might have, so for example, if you have for a fixed MSE, you could have high variance, low bias, or you could have low variance, high bias.